I'm Ivan Perez. I'm from the FP Lab at Nottingham, and I'm going to talk about game programming and testing games. So first, this is what we're talking about. We're talking about Haskell games running on desktop or mobile, and what we want to answer is, how do you write a test for something like this? What does it mean when the test is passed? And also, if your user sees a bug, how can you reproduce that bug? So the vehicle, the way that we express games in Haskell is using FRP. And there's far too many flavors. It's a wide field. But just to give you an understanding, the idea is to express that things change over time as functions from time to value. So for instance, the mouse position is something that changes over time. So it's a function that at any time will give you a position. And so is an animation. An animation is a picture that changes over time. And you can express an animation that depends on the mouse position, which is, for instance, in this case, a circle, which is always at the mouse position, by defining a function that at any time is a circle at the position of the mouse at that time. And because you have access to the time, that you can do calculations based on time. For instance, instead of being the mouse position, you could make it move around the mouse position as time progresses. And there's no time deltas here. There's no sampling, there's no notion. Time is continuous. And as you can imagine, this is really useful for games. And these signals, which other FRP flavors call them behaviors, these signals are functions. So they are referentially transparent, and you can do equational reasoning. You can do things like this. And there would be an expectation that even though you're talking about the mouse position, which comes from the external world, you can do something like that. But because you have access to time, then you can also do nasty things like this. You can start asking for past values, which means that you need to remember past values because we're talking about mouse positions. You can't actually calculate it. So this kind of structure would leak. And if you do something even nastier like this, you will be looking into the future. And of course, FRP implementations limit what you can do with respect to time. But we still have that mouse position over there. And different FRP implementations give you different ways of accessing the outside world. But there's a common theme for many of them, that they all use I/O in some way. So they either use I/O for performance or to access the external world, or both. And the problem with this is that even though signals are referentially transparent and I/O in principle is pure, you can't duplicate the real world. So if you want to rerun a test, you would need to clone the real world, but you can't. So this is not just based on user input. You also have a problem just based on sampling. So for instance, this is a picture of a force-directed graph layout algorithm, which means you have a bunch of nodes that compose a graph, and they all repel each other, but the ones that are connected also attract each other. So they form kind of like a spring. And you would expect some of these configurations to stabilize, but they don't. Even though there's no randomness, there's no user interaction, they don't stabilize because they're too dependent on floating point calculations. And the moment that the time deltas are not fixed, this converges to different equilibriums. So you need somehow to avoid I/O, even though what you're doing is essentially I/O. And the vehicle that we use for this is ROized, pure ROized FRP. And the idea is that instead of defining signals, we define signal functions, which just transform signals. So this is very similar to what we had before, which is this. So here, we just make the mouse position an input signal. And based on the mouse position, we produce an output signal, which is an animation, a picture of a circle. The difference here is that the mouse position is a variable. We could call it whatever. It doesn't matter. It doesn't actually come from the outside world yet. So there is just a variable. And we still have access to time. And the good thing about this kind of construction, this pure ROized FRP, is that it deals with both problems that we're trying to deal with. One of them is time, because it doesn't let us sample things at arbitrary times. It enforces causality and avoids leaks by construction. And at the same time, it's letting us keep the I/O part kind of like out of our construction. And you'll get a better picture of all of this here. This is how you run it. So how you run it is you have a computation that gives you input samples and times, and it always progresses towards the future, and a computation that consumes the outputs, and then you run your signal function. But the signal function is pure. There's no tricks in the implementation. There's no IRFs, nothing special. It's absolutely pure. So since we have this, which gives us a way to run a test several times, the question now is, how do we express these temporal properties? And the obvious answer is temporal logic. So what we can do is, we can of course have a signal function that produces a Boolean, but we can also use normal things in temporal logic, like this is always going to be true, this is next going to be true, this will be true until this other thing is true, and so on. And then we have a way of evaluating these predicates, which we just give it an input, a bunch of inputs and the times when they occurred, and we give a temporal predicate, and it tells us true or false. For instance, for something like this, it says we have a tuple, the first component is greater than the second. Is this true? And the answer is, for this stream, yes. For that stream, no, because the first component violates the property that you're trying to test. But generating these streams for real games is insane. There's no way that you can write them. So we turn to QuickCheck. And then QuickCheck can generate these streams for you. And we have a bunch of combinators or generators for QuickCheck that allow us to generate streams based on the time deltas that we want. But just to show you how it works, it's exactly the same interface, only we call QuickCheck with it. And it immediately finds counterexamples for the properties that we're trying to test. And it seems like this is very elementary. This is almost nothing, but it's actually useful. And we have a game, it's open source, it's called Haskell, which is an Arkanoid Haskell implementation. And one of the properties that we wanted to know is the ball always within the screen boundaries? And we ask QuickCheck. So is the x coordinate of the ball always between 0 and the game width and the screen width? And QuickCheck said, no. And it started giving us a counter example. And it said, well, there's a first sample, it doesn't mean anything, but then there's a second sample that throws the ball up into the air. And then there's a third sample, which occurs 12 seconds later. And what it means is it's saying that you throw the ball and then you wait so long that the ball is already out of the screen. And this actually points to a problem with the physics. It's a non-trivial problem with our program, which is that we're not doing continuous collision detection. We're not detecting when the ball will collide with the wall and then forcibly simulate at that time. So if we have something really thin, like a block, and the ball is going towards it, we might sample here, and then here, and miss the collision. And for the user, that just went through. That's called it's a well-known problem in game programming. It's called the bullet-through paper effect, or tunneling. So apart from this, facilities for tests in games, we also have two other things for debugging games. And I'm going to very quickly show you the first one. Yeah. So the first one, what it does is, because because the reactivate function is so simple, we can very easily dump all the inputs into a file and then reread them. And that's precisely what this does. We just record the game input and do whatever. It doesn't really matter. And this is just saving everything that is happening in a file. And now we can replay it. Yeah? There we go. Wait. Now we can replay it. And I'm moving the mouse on the right-hand side so that you can see that it's not actually, I'm not actually playing the same thing. I'm not that good. So you can replay it again and again. And it's guaranteed to be the same thing. So based on this, we have built one more thing, which is an interactive debugger. And what this does is it allows us to run a game. Let me see if I can. There we go. And see it run step by step. And the difference is that here we have a guarantee that it's going to be reproducible. It's a guarantee by the type system. So we can go back in time, and it's exactly what we saw before. And we can also travel to a particular point, and that's exactly what we saw before. And we can save the trace, and then we can pass it to quick check. See? We can pass it to quick check, and we can start, well, we can open it with GSCI and start testing properties the way that I explained before. And, excuse me. For instance, here, what I'm doing is I'm testing the property that I mentioned before, except that I'm just checking whether the ball touches the floor, like overlaps with the floor. And it says it does. For the trace that I saved from the simulation that you saw before, the ball actually overlaps with the floor. It goes into the floor. And we can ask quick check, can you give me a simpler trace? Because maybe the test that you run with your game is really long and it's really hard to understand what's going on. So you can ask quick check for a simpler trace. And is this what's going on? Wait a minute. Oh, wait. Yeah. What's going on? Yeah, sorry about that. So you can ask quick check, now you give me a simpler trace. And quick check gives you a trace with 4 samples. And this trace is compatible with the interactive debugger. So you can load it back, and you can see it, and you can see the ball in the wall, which means your tester, which is in a completely different country, tells you that there's something wrong with the game. And you only have to save the trace. And if you have the same floating point arithmetic, you are guaranteed by the type system to get the exact same result. If they see a character's head in a wall, you will see the character's head in a wall. So the umbrella project for all of this is called Haskell Titan, which stands for Testing Infrastructure for Temporal Abstractions. And it includes the facilities that I just talked about, plus that this is very easily accessible from Cabal, which means that you can run these tests every time, well, directly from Cabal, and every time you deploy. So this can be part of your test suite. And the testing facilities itself, the quick check and testing stuff, is in Yampa's repository. Yampa is a functional reactive programming implementation. And the debugging facilities are in Titan's repository. And there's a few other things in the paper. It gives you ways to combine different streams. It gives you ways of generate other kinds of streams with smaller, more realistic time deltas. And even though I'm talking about testing games, you can use something like this to test the FRP implementation itself. For instance, to check that your signal functions are actually arrows, and they are commutative, as you would expect. These days, it seems like everyone has their own FRP implementation, so I'm curious to see if it would work with yours. The debugger itself is not linked against Yampa. It doesn't know anything about Yampa. It knows about things that progress over time. That's it. It uses Telnet to communicate, so it works on desktop and mobile. So we have actually Haskell games running on mobile, and we can communicate with them. And the user interface is OK for smaller traces, not yet so good for 20, 30, 40 minutes of game run. So we're working on that. It also consumes a bit too much memory for my taste. Yeah. So this is being used in production. We have Haskell games for mobile and desktop. The one on the left, Haskenoid, is on GitHub, and it works on Windows, Linux, Mac, iOS, Android, and web. And except for web, the code for everything else is the same. Even the backend is the same. It uses SDL. And you can interact with it with a Wiimote and with a Kinect. So if you have a Kinect at home, you can plug it in and just move it around the room, and it will see you. The one in the middle is one game we're working on. It's called Pangalanda at the moment. Of course, that will not be the official name. And it's on Hackage, so you can contribute to it. And it uses time travel, by the way. So because FRP is a temporal abstraction, it's not so much about reactivity as it is about time, this game can let you travel back in time and then travel forward within reason. And the one on the right is a commercial game, and it is on iTunes, and it is on Google Play. And it is written entirely in Haskell. And the code for both is actually the same. The code for both Android and iOS is the same. And it works on desktop too, although I don't distribute it for that. So just to very quickly summarize what we saw, the idea, what you need to take away with you is that what we opted for is, instead of looking for an FRP implementation that is very tailored to performance in games, what we do is we go for something that is purely functional. And instead of trying to write the most complex games, we write simple games and see where the problems are. And we also see where the benefits are. And in a real game, the budget for programming is something like 30%. I've seen budgets that were below 10% for programming. But testing is a big thing. And if you can tap onto that part of the budget, that makes a big difference, because it's really hard to convince a company that they should opt for Haskell when a 10–20% improvement in the programming productivity is a 6% improvement overall. But if you say that, well, you have thousands of players, millions of players, and you can rerun all your tests and make sure that new changes will never break anything before you deploy, then that is a big thing. And yeah, just to summarize, what we see is that we can very simply write temporal tests. We can quick check interactive applications, and we can actually see quick check play the games. We can see quick check how it runs forward and finds the bug for us. And this works also for mobile, which means that we have a way for users to send us the traces from the games remotely, which means that we can reproduce bugs locally as long as the architecture is similar enough, and that means the floating point arithmetic is similar, is the same. And well, that's pretty much it. Thank you all for your attention.